With synchronous serial protocols, the devices share a common clock signal. So typically one of the devices acts as a master and the other or others act as slaves. So each bit of data is sent on a clock edge. So the clock basically keeps the communication in sync. So every time the clock ticks, one bit of data will be sent between the master and the slave or vice versa. So examples of common synchronous serial protocols include Integrated Circuit or I2C, Serial Peripheral Interface, SPI, and also very common protocol that we use is the USB, so Universal Serial Bus. So each one of these has got a clock signal as well as the data lines. So with I2C, there are two lines on the bus. So you've got the serial data and serial clock, but just as the case with UART, they need its voltage levels on these lines which represent ones and zeros, so they need to share a common ground. So typically there will be three lines. You've got your two data line, a clock line, and then ground as well. So the lines require pull-up resistance, so the pull-up resistors. So you can see here between the data line of 3.3 volts and the clock line, there's some pull-up resistors. And also, there can be multiple slaves on the same bus. So with I2C, each slave has a 7-bit address. So you can have 127 different slaves connected, all with the same two lines. So or three if you include ground. So you just write, when you send data, you send it to a particular address and it'll just go to that slave with that address. So there's several clock frequencies that are standard, so 100 kilohertz, 400, 1 meg, 3.2 meg. So you can see this is quite a high frequency communication compared to UART. Another very common one is SPI. So now there's at least 4 lines in an SPI bus. So we've got a master out and slave in, or MOSI, master in and slave out, it's meso, the stereo clock, and the slave chip enable. So you can see as an example we've got 3 different slaves. So the MOSI, meso and clock, these are all common lines between, so they all share the same lines. But then each slave has got a different slave chip enable, or sometimes called a select line. There's different names, so each one of these has got a different line. So they use the same lines to transmit the data, but when you want to send, for example, we call it slave 1, 2, 3. If you want to write to slave 2, you'd write a 0 to this one, so a 0 to this one, and a 1 to this one. So one of this slave will be enabled. So when you sent a message over MOSI, even though it was going here and going here, this slave would know not to respond because the chip enable has been set to 0. So SPI, you need more lines than I2C, but it is possible to get much higher clock speeds. So let's briefly mention the duplex communication. So this is when communication can happen in both directions. So SPI and I2C are both duplex systems, so we can send from master to slave or slave to master. And then a full duplex system is one where two-way communication can happen simultaneously. So SPI is full duplex because we've got this MOSI and meso line, so communication can happen both ways. We've got separate transmit-receive lines. But I2C, there's just one common data line, so SDA. So one data line is called SDA. So that's only half duplex because the master can't send data to the slave at the same time as the slave is sending data to the master.